Okay, we're going to get started. Kurt, is that Mike? Um, good morning. Good to see you all again. I appreciate your patience during all the work we did together yesterday. I thought I'd start today, as I try to most days, with a bit of a retrospective on what we saw yesterday. It can help you integrate together some of the many concepts and perhaps get you ready for today's exercises, particularly for the project in the afternoon. So yesterday, after a bit of orientation at the beginning, we turned to look at an initial model which exposed you to several things. One thing was the any-logic interface for conducting modeling. At a more fundamental level, it exposed you to some basic concepts involving agent-based modeling. The notion that we can use a model to characterize the current state and the evolution of a population over time. So we had individuals within this model, their behavior over time characterized using a construct, in this case called a state chart, whereby they would progress from one state to another. The logic of it was not emphasized in that lecture, but we saw it later in the day. And we put those individuals, each of whom evolved in this way, we put them into a situation where they weren't solitudes, but instead where they interacted. They were placed in an environment. The environment in that case, like the model itself, was particularly stylized. Keeping people packed into a regular grid where they interacted with their neighbors in north, south, east, and west. And each individual here went through their progression over time as influenced by those neighbors. And we saw that while we could drill down to the level of the individual, some of the most interesting things that were happening were patterns that played out at the macro level. Patterns that exhibited regularity, but some stochastic variation within them. In this case, it was a situation where we had this kind of expanding circle, as it were, expanding oval, which expanded from the point of where the first agent was expected and eventually consumed the entire space. And I noted that was an aspect of emergence. This is a feature of the situation that resulted dynamically, something that evolved over time, and involved spatial components that was in no way directly programmed into that model. And nowhere in this model did we say, let us create this regular structure we saw. Instead, it emerged from a diversity of different features of the model. Indeed, from contacts between individuals spreading the infection, but also from the fact that they evolved over time between multiple states, the fact that they were communicating with nearby neighbors rather than with just anyone within the space led it to spread in a sort of regular way. So this gave us a brief glimpse of the use of the tool. We saw that we could define these experiments of sorts, experiments that could investigate different conditions, for example, some baseline situation, sort of base case, default situation, and then a situation where we changed our assumptions and we're assuming instead a slower recovery. We saw that many of those experiments could be specified by changing assumptions to the model as specified by parameters. We saw in the any-logic interface that you could select something from the model, see its properties, and then you could change assumptions by going in and editing these properties. So that allowed us to run several experiments with different assumptions. We then did something, undertook a more fundamental change, and that involved changing the structure of the model, changing the assumptions about how the world works is captured by the model. These models capture a dynamic hypothesis, sort of for how things are playing out in the world, and we can alter those hypotheses, examine the impact of other hypotheses, perhaps counterfactual, and see their impact over time. And in this case, we made a simple, conceptually simple modification. We allowed people to go back from recovered state to successful state. In other words, we allowed for waning immunity. And we examined the impact that had on model behavior. And we saw that its impact, although it was a fairly small change, its impact on model behavior exhibited was fairly profound. Rather than seeing just this expanding oval which took over the entire space and left everyone recovered, we saw now we had multiple generations, as it were, waves of infection, with one wave seeding the ground for the next wave of people who are recovering again, or were losing immunity to get infected. So we saw that a minor change to model structure could profoundly alter behavior associated with the model. And indeed, this illustrates the principle that we sometimes talk about in complex systems of structure determines behavior. But changing the structure of models, say our assumption about the natural history of infection in this case, it could lead to significant differences in the behavior exhibited over time, temporally, so the dynamics of the system. We could look at this at the level of the whole space. We also saw later in the day that we could very easily create charts which would count, say, the number of people susceptible, the number of people infected, the number of people recovered at a given time, and show a graph to us in that sort of aggregate manner. So one of the nice features of these agent-based models is we have recourse to a very fine-grained, low-level depiction of the situation. We could drill down to the level of an individual person and check what they're doing, but we can also zoom out and see information about the space as a whole, or indeed characteristics summarized across that entire space, such as the count of people susceptible, infected, and recovered. And that's a powerful feature of agent-based models, the ability to zoom out, to summarize things, to slice and dice it in any number of different ways. And for those of you from backgrounds such as EPI, anyone with background in demography, etc., will appreciate the value when you have a modeling framework like this, not presupposing a particular way of dividing up the population, such as everyone is divided into 5-year age categories only. Instead, to allow people to have their age summarized across any number of different metrics. You can break it up where required into 5-year age categories, other times 2-year age categories, other times 10-year age categories, other times 3 age categories. It's a very useful feature of agent-based models that allows us to make use and compare them against empirical data. Okay, so we saw that initial model, and it helped expose us a little bit to the any-logic interface. Occasionally, agent-based modeling has long been the province of those with significant programming skills. And upon encountering this sort of representation, some of the questions I'll frequently get are, is this a toy interface? How far can this really take you? If you have to create a real model, can you really use pictures like that? And the answer is yes. So we have very large-scale models, and a fundamental mode of interaction with them is interacting with the state charts, interacting with these visual depictions. So it's not merely something that only works for small toy models. It's something which scales to much larger models such as I've given you. Okay? So those are some points from that first lecture. I wanted to now continue on and reflect our progression by looking at the second lecture. And here we talked about a variety of motivations for agent-based modeling. I had noted that some of the major motivations are listed here. These are not all, and in fact, later I'll talk about some additional hallmarks of when a complex systems approach might be advised. But here we noted the importance of dealing with situations where you sort of causally tangled pieces. You think about health disparities in this country, and you have issues that run the gamut from opportunity structures, residential segregation, income income-derived and racial segregation, aspects concerning educational opportunity and the role of wealth in opening opportunities for education, to factors having to do with health and having to do with the impact that ill health can have in shaping someone's trajectory, the impact of early life exposures on later life outcomes and early insults and shaping one's later life. All these things tangled up together. We talked about multiple sort of health ecosystems like obesity and tobacco, where there are multiple actors interacting sometimes in ways that are seeking to thwart each other's efforts. Reciprocal causality, feedbacks, where we have vicious cycles or virtuous cycles. For example, where early deprivation, lack of opportunity for wealth can limit your educational opportunities and further limit your ability to secure a stable income later in life. We're formulating novel interventions where we don't have good statistical data. We want to prospectively evaluate them. Cases where there's adaptation and learning, where networks play a role, and where we want to balance upstream and downstream effects. All of these are potent sort of motivators for the use of these sort of effects. This is going to link in with a list I'll be showing you later on sort of hallmarks, flags I look for when I encounter a problem, like we're listed on the board last night. I look for certain features of the situation as an indicator that a complex system approach or a system science approach is really advised, that it's needed, that it's desirable, where it fits in. And I'll be going through a list of those later, but this provided some motivations there. We then went on to talk just a little bit. I highlighted some features of the modeling process related to triage, a fair bit of that material. And I noted the importance of incremental model development. If there's one lesson you can take away from sort of a picture on how we build models, it will be the fact that it's best to build them step by step by step. One of the biggest dangers of agent-based modeling, I noted yesterday, one of the biggest weaknesses, you can think about it, is its the ease of adding new assumptions, features, pieces to your model. It's incredibly flexible, and that's both a strength and a weakness. A weakness in this case because it's always easy to throw in another thing without giving it much thought, without the gravity of consideration it deserves, and you find that that your understanding of what's going on in the model has been obscured. You find that the clarity you brought might be lost. And this is a danger specifically and primarily if you're throwing these things in all together before you get the model really built. If you add them one by one, it's fairly easy to add something, examine its impact on the model, examine how does this change things. I add this feature in, and you could take it out or leave it in as desired. That's a fairly safe type of experimentation. What's dangerous is if you say, we're going to build the biggest model, the biggest, best model that's ever been built in this area, and a year from now we're going to have that model in hand, and we're going to figure out what pieces to go into it all ahead of time, and a year from now we'll finally be able to run it. That's extremely dangerous. Lots of people do it, and lots of successful projects have done it, but even more have failed because of adopting that strategy. And the real risk here is, if you do that, you end up with a model that's at the least okay, that may have quite a few bugs, but you can't distinguish those bugs from actual emergent behavior, because bugs are surprising. And it takes a very long time to get it running, and sometimes your estimate of a year turns into 2 years, 3 years, 4 years, and the model is not current by the time you create it. What's a much more effective strategy, and a strategy that I would thoroughly advocate for anyone in this room, is to take a very step-by-step approach. Start with the most simple, stylized model you can, and add pieces in one by one, observing the effects. That allows you to quickly localize problems, identify novel dynamics, and perhaps most importantly, learn. You learn over time from the model building process. And you may have, and very importantly, at all times you have some model. You have some particular model to which you have recourse. So you'll always have an asset in hand. Now, a year from now, you may not have gotten quite as far as you thought you would have originally, but you wouldn't have gotten that far in that year if you had decided to put it all together in the first place. You may have gotten less far within that first year than you would have liked, but you have something concrete, it's something you understand, it's something you're confident about because you've added things in piece by piece. And it's moreover something that maybe you have incorporated much learning that went on in that first year. So it may be a rather different model than you would have anticipated because you've learned from the whole process. You've learned what's empirically working, what's at variance with what you know about empirical data. You've learned what adding what things really led to interesting effects, and you've been able to incorporate that in shaping that model in the first year. So adding things step by step in these models is key. And I tried to emphasize yesterday a corollary to that in terms of when we build these models together, just constantly trying to rebuild them, run them, observe, and make modifications in a little incremental way within even a given session. A key step of this is each time we add something, we compare it with what we've seen previously. Sometimes we even disable the new feature, just make sure we haven't thrown things out of whack, and then enable it and do the comparison. So this incremental model development is extremely important. And I talked yesterday about a threefold division, and I want to probably go to the slide, but the threefold division between three types of things. Things that are endogenous, things that are actually simulated endogenous. These are things that are simulated by the model that result from the model. The model's actually generating them for you. Things that are exogenous, they're represented in the model. They impact things in the model, but they presuppose, you're presupposing certain patterns for them. They have fixed assumptions, not necessarily constant, but in the sense of fixed in the sense that they're pre-specified. And things that are ignored. Preferably consciously ignored. We create a list of them. We have deliberately omitted from this model of childhood obesity a representation of the impacts of in utero exposure on insulin resistance, something like that. You explicitly leave it out. You consciously do so, and you list it so that you can later reflect, do we want to add this in? Is there something we need to think about? And over time, things tend to move between these categories. Sometimes, a lot of the time, things that are exogenous move to endogenous. We add them in, step-by-step fashion. Sometimes you do the reverse. Sometimes it isn't that fruitful, and you take it out of the model. Some of the things that are ignored sometimes move to the exogenous and even to the endogenous state. So incremental model development is the name of the game for sane, safe, reliable, and insightful model building. And I would advise that very strongly to anyone here. It's a type of approach that use of any logic makes very easy, and don't fall prey to the bigger, better, or far off model. Okay, so we then went on to talk about a variety of technical topics, and perhaps I pushed you a bit too quickly yesterday. We actually created a variety of models here. The first actually looked at creating a population which exhibited heterogeneity. And within this population, we had individuals distinguished by several characteristics. They were assigned a sex, which was drawn from either males or females, using this kind of option list we added. So we had males and females in the population as a characteristic named sex, and then we assigned them an income. And initially, these two were assigned independently, so we picked a random sex, and we picked a random income, and we saw how we could, in any logic, use these sort of so-called functions. You could call up to them, and they do work for us. And in this case, calling this log normal function returned value samples drawn from a log normal distribution according to these parameters, mu 11, sigma 3.5, and min value 0. Similarly, we drew sex, and we learned a little bit of Java syntax here. We flipped the coin, and if it was head, it was female, otherwise it was, person was male. Initially, these were independent. I later, in comments to Ben, indicated how we could very easily, for example, have conditional probability distributions. You could have people's income be drawn from different distributions, whether they were a male or a female, for example. Very, very readily done, but you need to add the parameters in the right order. Okay? So we saw this, and we saw that if we ran a model like this, we could go and create a situation with a diverse population. Each population member, if we drill down to this level, has a sex and an income, and that varies between different populations. We moreover use this as an opportunity to see how we could make the visual representation of a person, their representation, say, using an oval, to distinguish aspects of their characteristics. So in this case, we gave them these properties, heterogeneous properties of sex and income, and we made the color of that circle be reflective of sex, and we made the size of the circle be reflective of income. How did we do that? Well, some of you may remember, within this framework, it's what we call an object-oriented framework. If we want to set the characteristics of something, we go to that thing, and we tell it what its properties should be. In this case, therefore, we're talking about the properties of a person, and specifically about the person, their representation. So we went to this oval, and we saw that we could set its color according to some formula, a bit like the formula you use in Excel, for example. And we saw that we could set its radius according to a different formula. And any logic takes care of all the how. Even if income had been changing, the size of the circle could be automatically changing over time. But we saw we could put in little formulas like this. They're called expressions in Java, and that it would take care of kind of doing the necessary plumbing to make that happen. This is what we call a declarative system. We specify the rule for fill color, and it takes care of accomplishing that. So this is a little model which exhibited heterogeneity. It exhibited ways in which we could set people's appearance based on their characteristics. And we saw, moreover, that these parameters could be applied at the individual level, or indeed, ladies and gentlemen, at the population level. So we introduced a parameter at the population level called population size. And that parameter allowed us to vary easily the population size associated with this model. Now, if we had a person, the value of that parameter, the things to assume about that person in terms of their sex and their income, were specified in the population, because that was responsible for creating them. And in fact, this shows the modification I made for Ben to show that income based on someone's sex. But if we have an assumption, say about population size, that applies to a model as a whole, it's not an assumption about a person, it's an assumption about the whole population. That parameter lives in main, because it's something main keeps kind of track of things involving the whole model. So population size lives here, and who specifies it? The experiment. So each experiment, we can make different assumptions about population size. We need one experiment where we had a modest population size. I think I'd run that just a moment ago here, something like this. And then we had a population which, and then we had another experiment which had a 10,000 person population. And in this case, we had a population that was much larger, exhibited the same income gradient. Over here, lower income people. Over here is the Beverly Hills of our model, with high income individuals. But this is the situation which exhibits for different of these experiments. We could pose different assumptions about the model, And those assumptions can be communicated by these parameters, such as this parameter in main. Okay? So we introduced these parameters, and they were operationalized in terms of making the population accordingly. How did this population size get actually operationally realized? Well, we have this population, which represents the population. We simply said the initial number of agents is given by this parameter population size. So that's how the value of this thing turned into the size of the population. That's one the number of agents. So that was an initial model. Wow, you went through a lot there. And I appreciate your patience with that. And I was impressed by your resilience. I was impressed by your ambition. And in the next exercise, I pushed the envelope further, and you continued to exhibit those same features, but I think I pushed a bit too far with this later example. So that model we just examined was great. It exhibits heterogeneity, it exhibits very distinctive visual properties, but there's no dynamics associated with it. No one was evolving over time. And in our next little vignette, we examined a situation where we had people evolving. We captured the evolution of individuals over time. And how did we do that? We did that by introducing state charts. State charts are not the only means by which agents can evolve over time. We'll see other mechanisms today, events. We'll see later mechanisms later in the week. We can introduce stocks and flows, system dynamics components into this model, and have people evolve according to those in a continuous fashion. But here, state charts are very fruitful for representing certain types of conditions, particularly where we have, with respect to a given concern, say someone's weight, we have a set of categories that are collectively exhaustive and mutually exclusive. Normal and underweight, overweight and obese categories, for example. So each of these state charts represents a person's current state and the evolution of that state. Evolution is being dictated by these transitions here between these states. A given state chart is focused on a particular type of concern, in this case weight. On the right-hand side here, their status vis-a-vis diabetes. And these two state charts can coexist. The right one keeps track of are they diabetic or not. The left one, whether they have what their weight level is. And a given individual will start in a given state here. In this case, we made the particularly simple assumption. This is a little toy model we built up together, that everyone started normal and underweight, normal glycemic. In general, we could distribute people among these categories initially. Very easy to do. And then people evolved over time. And so we had people going between these states according to certain rules. And once again, any logic allows us to dictate those rules declaratively for a wide variety of rules. And we saw that there were a wide variety of transition types. In this case, we have a rate transition. A certain chance per unit time of going from this normal weight state to the overweight state. And what is that chance per unit time? It's 5% per year. So you have, this is continuous time by default. In other words, you can break time up and as fine components as desired without trouble. Some things can be going on really quickly and some things more slowly if desired. It takes care of all of that. In this case, it's 5% per year. So on average, the residence time of this state is drawn from an exponential distribution. It's exponentially distributed. It's a memoryless process for whom that's a meaningful statement. And it's stochastic. So the exact time that a given person will go from this to this will differ from person to person. It's like it's based on the roll of the dice, the draw from an exponential distribution, when they'll leave here. With this natural time constant. So 5% per year. And so people would evolve. Now, however, in any logic, we have a variety of types of transitions. This is one of about 6 types of transitions. Others of them are timeout transitionals. We actually examined where someone, it's the opposite of memoryless. It's completely memory full. They leave exactly a certain time after coming in. We could specify that time to be some fixed number, some constant, or it can be drawn from the distribution if we want to have a custom distribution for how long people stay at state. We just saw a fixed rate. We could have a variable rate transition. We saw that in this example. I'll show you in a minute. The transition can be dependent on other things, such as some condition, such as when an agent arrives at a destination, having moved, and as we'll see later this morning from that distribution. So we have these types of transitions, and we can pick them within any logic, these different choices. And in this case, we were making use of a particularly simple one. Now, where I really pushed the envelope, I had the occurrence of a given person in one of these states be indicated visually by a color. So when they enter the state here, they acquired a certain color. So when they entered this state, they became green. And similarly, when they entered this state, they became yellow. When they entered this state, they become red. Now, how is that assigning this to color actually operationalized? Well, we actually had the fill color of this circle be specified to be whatever the value of this variable is. So if we make this variable green, boom, that person, their color becomes green. And so we, running this, what we saw was a situation where people were moving between various categories according to their color. And their color here indicated in which category they were located. As soon as they became obese, their color, as accomplished through this variable here, color, was set to red. Okay, so people were moving between colors, and that was accomplished by, again, the property of that circle. They made their current color is captured by that circle, be dependent on the variable. Okay. The other thing I did here, which added perhaps insult to injury for some people, is I introduced a situation where the two state charts interacted. So this state chart here actually, the likelihood of transitioning from here to here changed based on which state they were in. How did I accomplish that? Well, conceptually, it was the same mechanism I used for color. When they entered the overweight state, well, if they entered the normal and underweight state, they'd have a low chance of going from here to here. When they entered the overweight state, they would have a much higher chance of going from here to here. When they entered this state, they would have a yet higher chance yet of going from here to here. So their chance of going from here to here was set by this variable, diabetes hazard, and that variable held different values depending on whether they were in this state, or this state. What this meant at a concrete level is that if they were obese, they had a high chance of becoming diabetic while they were obese. If they were overweight, they had a higher, significant chance of becoming diabetic. If they were normal and underweight, they had a low chance of becoming diabetic during that time. So I was trying to show here that these state charts are not solitudes. They're not independent of one another. You can make one influence the other. In fact, we could have made it bidirectional. We could have had, the likelihood of transition between weight states depending on the chronic diseases a person has. So if they have heart disease or chronic heart CHF, it could lead to changes in their ability to exercise, etc., or their motivation for exercising, and that might change their likelihood of transition here. So this is readily accomplished, but it's an awful lot for a first day. So we saw these two state charts and their interactions, and we in fact accomplished that. And I was grateful that you didn't all walk out of the room and never to return. Wow, got pretty far actually with that. Finally, at the denouement, as the final capstone of this exercise yesterday, we added statistics to this model. We actually kept track of how many people there were in each of these categories. And how did we do that? How was that accomplished? Well, we actually went into this population, and we saw that within a population, you could define statistics of your choosing. You could either add statistics, again, the population was in Maine. That's where it lives in this case. So we went into Maine, and we went to the population. We found there's this whole statistic here. We could say add a new statistic and define a statistic. We defined the prevalence of obesity, prevalent case counts for those who are obese, and it would count up the number of people matched some condition. Introduce that condition. That meant we were counting up obese people, and that gave us the statistics we could use. And defining that statistic allowed us manifold advantages. And if we run the model, most notably, with that statistic at hand, we could go click on this population. We could actually see over time, okay, how many people are obese, for example. What's the fraction that are obese, etc. So we could define these various statistics. Another thing it afforded us is an easy way of building these charts. And one of the nice features of any logic is both those can be accomplished in this declarative way. We specify essentially what statistic we want it to compute, and it will take care of making that happen. What chart we want the chart to show, and it will take care of making that happen. In this case, we told this chart, we added this chart, we told it, hey, display the fraction of these. This is our statistic. This is what we built. This is our thing, our contribution. We brought that to the table, and we told it, display that statistic. And display it did in the chart. We simply say, oh, also display the prevalence of diabetes. And it went ahead and did that. This is the statistic we added. We just gave it its name, and we bowed to the job by God by having it, by calling one, right? So that, ladies and gentlemen, was how we accomplished showing output from this model. And I noted there's many other forms of output we'll talk about this week. This is one of them, but it's a particularly powerful, accessible form within any logic. Okay? So that was our final exercise, and it was perhaps the coup de grace. But it got us remarkably far, I think, within the first day in terms of exposure to things. And like the Bach fugue that I try to emulate, we'll come back to these points to try to build up those skills in coming days, but in a less aggressive way. So I appreciate your patience yesterday. That was, I think, by a significant shot, the hardest section of the boot camp. And I am appreciative of you bearing with it. Today we're going to learn some new tricks, reinforce the tricks we've already learned, and finally we'll push further on those projects. I do have some comments on the project. The TAs and I spent some time discussing some features of the situation, but I'm going to reserve my comments on those till this afternoon when we have project time allocated. And we'll go through, discuss these things, and with those comments fresh in your mind, we'll meet with the groups and try to advance the particular project idea. Okay? Questions?
Yeah. I noticed several times you see the name
Yeah.
and title.
Yeah.
Can you tell us is this something that you can say at another time, like really just a naming project that is very specific?
Okay. You mean like title?
Yeah, because you see this, I think you see this in different places. Right?
That's true. Yeah, you could actually, the title does not, if I get what you're asking, the title does not have to be set ahead of time. So is that what you're asking? Or?
I'm just thinking, is this specific to this statistical procedure at this time?
Oh, okay.
Or is later we were to add something and build a slightly different model? We're talking about adding, incremental.
Oh, yeah.
Can we pull this up using that name? Is that the purpose of the name?
Yeah, so you could readily add additional statistics to here as the model develops. It's not something you have to do up front. Mm-hmm. And so maybe, in the first month you'll add 2 statistics, and then you discover, oh, we have empirical data on this or that. We could pull data from, the MPAINs on this certain thing. We want to compare it with model output. You could add 3 more statistics later.
It shows you, yeah. I guess, I think that I'm thinking of it, but when you write stats, you have macros.
Right.
So it's kind of like analogous to that concept.
You can think of it as that. It's very easy to do things that are a little bit more analogous yet to SAS macros. over here. You can readily add in what are called functions, for example, to your model. In this case, these are particularly simple things to define. They're a little bit more akin to Excel formulas or something like that, in the sense that these statistics, like this fraction obese, that came from defining over, defining over here in the population, this population here, this thing, fraction obese. So this statistic, we can add this in, and that's completely defined by these two lines. It's defined by this condition. What things do we want to sum over? What people do we want to sum up? And for each one, what's the value we want to sum up? And that completely defines it. We don't have to write any more code than that. By contrast, there's also a very powerful mechanism for actually adding in something more similar to SAS macros, where we might have a long section of code. We can add that using a mechanism over here that's called, for example, if I were to go to main, I could add in, I'm looking in the wrong place here. I could add in from the palette up in this general, I could add in a function, and that will actually allow me to do something much more sophisticated all at once. That helpful? Yeah. And finally, there's this is pursuant to Ben's questions yesterday. If you have external packages, maybe the statistics packages externally to define, any logic has a large set of built-in statistical functions, but I may want to use some custom statistical function that's not defined in any logic. I can easily call off to what are called external libraries, and there are literally hundreds of thousands of Java libraries available for various tasks, and a significant number on the statistics side. For example, the Apache statistics library, which I've used extensively, and I can easily call off to these external things. And it's very easy to set it up so that I can make use of other people's statistics libraries, or indeed pieces that other people have built as far as their models are concerned. So, for example, later in the week, Winchell here will be giving a little talk showing how anyone who uses AnyLogic could use some tools we've built up and use it to sort of simplify certain tasks with AnyLogic. And we make those tools freely available so people can make use of them. Okay, is that helpful? Mm-hmm. Okay. Any other questions? Yeah. Oh, okay. So X and Y axis here? That's a great question. I can answer at a couple different levels, and I'll try to hit a couple points. You can tell me if I've gone off the mark. Okay. So one thing we learned with these models is that that we can set people's location visually for various purposes. And for example, the first, the gender and income disparities, we had sort of this this depiction where the x-axis indicated an income gradient. So I actually located people on this axis according to their income, and the y-axis I just put people randomly. Okay. So here I wanted to connote something by the x-coordinate, namely how big their income was. And that was partly because Lisa yesterday had inquired about, could we have a separation physically between people who are high income and low income? Because we see in the world these properties like propinquity, where people tend to associate geographically, tend to be associated geographically with people who are like them, say, in income. Right? See a clustering of neighborhoods by income, for example. Wealthy people living together with wealthy people, and people who are poorer and have less means in life together with other people who are poor and have less means in life. So here I actually I captured that spatial layout, sort of where people are, made that vary with income. And in a lot of models, we use space to actually represent some feature of the geographic location of people in the world. AnyLogic has tools to work together with GIS systems, and you can actually impose, a map of LA or a map of St. Petersburg or what have you, and actually have people situated at corresponding locations. And AnyLogic 7 has gotten a little bit easier yet. And I have a model that, an example model, remember that one I showed you yesterday involving deer and their movement over the landscape? That model is geographically rooted. So sometimes we use these we use them in order to capture sort of geographic characteristics. In other cases, we use it to just sort of as a convenient mechanism to just show people, group people in certain ways. Yeah. Okay, yeah. Yeah. Oh, yeah. Okay, I'm sure. Thank you. So with respect to this, so here we have a person. This is showing a person. Remember, we want to keep track of what we're looking at. It says a person. So we know we're looking at a person here. And why is it that all these things are here? And why is it this circle is right smack at that place? Like, why did I put it there? Why not put it somewhere else? Well, this is okay. There's two issues that are somewhat different. As to why things are here, well, it's a matter of convenience, and I'll show you exactly what the issue is. So let me close this, and I'll close this thing with person over here. The one thing you'll find is that if I go click on person here and open it up, it tends to show me things in this lower right-hand side. So that in one model, or down here in this other model, it tends to show me these things, and I like them to be visible when I open it up. Now, I can go see them elsewhere. I mean, I can go scroll up like this. I mean, it's no problem. And look around. But it's just kind of nice if they're visible when I open it up. So that's a kind of convenience thing. It's not in any way privileged. It's not in any way cheap. It's just, I like to be able to see what's there. Now, as to why that circle is there, this is the, this is very effective. That circle is located there because that's the point of reference. So the fact that it's there means that if they're logically at a certain location are called 100 by 100, or something like that, a point x and y, 100 and 100. Then they'll actually visually appear at that same place. If I put this offset from that, say to the right, they actually appear at a different visual location than their logical location. So this allows you to create, AnyLogic comes with all sorts of different sort of things that you can add. It has quite a library here, and some of my students have gotten rather mischievous in employing some of these things, to associate with people. They created a model where the icons were rather sensitive for the shows my face. And the point is that you can create a representation of a person that's rather articulated. It may be a factory and you want to show it as sort of a larger thing or what have you. And this is just a point of reference, and it's often convenient to kind of have them logically appear, have their physical appearance on the screen be the same as their logical location. But you don't need to do that. It can help ease reasoning in certain cases where you kind of figure out why is someone there. You want to look through the locations of all people logically, and you'd like to be able to match them up to people on the screen, something like that. It's a very minor thing, but occasionally comes in handy to have something to say. Yeah. Yes. Yes. Yeah. Correct. It'll be offset from that point. Yeah, that's right. So you can go through and you can list for each person. What's your logical location? Oh, that's your true location. But this is just dictating visually where what do they look like, and I like to have them actually appear visually at the logical location, just so it's easy for me to figure out who's who or what have you in the model. It's a slight convenience thing. It's nothing terribly deep, but occasionally it's useful. I don't, that's helpful? Okay. Okay, great. Any other questions? I know we saw a lot yesterday, and I hope that by hitting on these couple points, it will help lay the groundwork for building on that. But any other questions right now? Okay. Again, grateful for your attention yesterday and today. Hope that was helpful. And now we will press onwards and upwards.